All right, so the topic of today's lecture is uncertainty and utilities. Last week, we talked about minimax algorithm and adversarial search when we have two players and one player is trying to maximize the utility, and the other player is trying to minimize the objective or the same utility. So one of the assumptions that we have in that algorithm or that scenario was to know that the adversary is playing optimally, meaning that his move is in a way that to completely minimize the objective. So we know that which path it will be taken after we choose our move with 100% certainty. For example, for this simple game, right, so we have two options here and two options over here. So we are the maximizing player and then the minimizing player here have a choice to do something. So based on the choice and the move that the minimizer make, then we choose our path to either go to the left or to go to the right. So to do that, we first simulate the minimizer or the adversary. So what is he going to do? So between these two objectives, then the minimizer has only one choice. So he chooses 10. And between these two, he definitely will choose a value of 9. So try to minimize that utility. And then based on this information that we are sure now that if we take, for example, this route, then the minimizer is not going to let us to have 100. And we're going to be ending up with number 9, which is something less than the left branch. Therefore, we choose to go to the left, preferring 10 somehow over 9. But we know that there is 100 over here, but we never get to that 100 because the player on the other side plays optimally, and we are aware of that. So this time, we kind of know that the player that is playing against us may not play optimally. So there's a chance of having utility number 9 to be chosen by the adversary. So there's a chance of doing that by the adversary. Therefore, we need different strategy than minimax. Because now, since the adversary is, there is some uncertainty or some randomness in his behavior by choosing this and this, then we can take our chance maybe going to this route. So in this lecture, we're gonna basically solve those kind of adversarial search that involve uncertainties. All right, so now we replace the minimizer with the chance node. So previously we had a minimizer, now we call it a chance node. All right, to do that, since we are talking about uncertainties and randomness, then there's going to be notion of probability involved. So therefore, we need to know the probability of somehow to find or approximate the probability of having the adversary choosing this or this. So if we have those probabilities, then we can use the algorithm called expect max to find the optimal path for our game and our next move. All right, so one of the situations that we explained that we needed the expect max was having an adversary that somehow may choose his action randomly, or there are some randomness involved in his move. So this is one of the situations that we may prefer to use the expected max. So the other one is to having the explicit randomness in our game. So somehow your games are like involving rolling dice, like backgammon game. So there are different kinds of situations. So there is one rolling dice, then the opponents act randomly. Then if you are taking example of those actions that we have in real life, we can refer to, for example, a robot that kind of measures some quantity, and then we needed those measurements in order to calculate our next move. So in best case scenario, we are assuming that those measurements are accurate. And therefore, in Minimax algorithm, so we kind of sure, okay, we have the assumption of having an accurate measurement in the process. But since in practice, any measurement involve noise or any actual physical activity in real world, there is some error involved in that process. Therefore, we cannot have a model that says, okay, with 100% accuracy, this is going to happen. So there are always error in the process. That's the reason expecting max is a better choice than the minimax in real world situation. Okay, so let's see how expecting max work. Let me change this view. Okay, expecting max search is kind of similar to min-max. The maximizer does its own thing as min-max. The minimizer is going to be replaced with chance node. For the chance node, what we do, basically, we compute the average score on the optimal play. So what do we mean by that? So for example, in here, right, so at this state, we are going to calculate the average probability of these two, the average outcome of these two. So if you assume that we are giving like half probability to this, half a probability to this, then the expected utility of this node is going to be half of 10 plus half of 10. So basically it's going to be, the value is going to be 10 over here. And then for this one, we also average the expected utility. If we assume that these two events are going to happen with equal probability of half, then the expected utility at this point is going to be half of 9 plus half of 100. Then it's going to be 54 something. And therefore now it's a time for maximizer to choose its utility. Right now, maximizer tries to maximize the utility. Therefore, he chooses this branch. And therefore, with equal probability at this branch, maximizer chooses to go to the right. But in min-max, it will choose to go to the left. So in min-max, the most that it can achieve is 10, but in expecting max, the max that it can achieve is kind of 54. All right, that's the process for expecting max. Okay, so for this one, so we have some demo for it. So we want to see how expect-max compare with minimax in real world scenario. For some reason. Okay, let's play this again. So this is a minimax game. In minimax game, so our adversary is playing optimally. Therefore, if they play optimally, this goes going to come in this direction, and this goes is coming to this direction, left. And therefore, since we know that they're playing optimally, to get the better score, it is better for the maximizer to jump into the ghost, because in that case, it takes less step, and the negative score that it gets is lower. That's the reason it's going to go to the ghost, and the score of minus 501. So if he chooses to go to the left, then the score gonna be a larger negative number. So this game is the expected max. Let's play it once. So we now assume that there are some randomness in the behavior of blue ghost and the orange ghost. Okay, so this one, this time the score is kind of lower. So the second time, if it's played, so let's see what is going to happen. So there are some randomness, as mentioned. Since the adversary is not playing optimally, then Pac-Man would be able to kind of score this game and get all those food. All right. So this is a pseudocode for expecting max. So if you compare this one with the minimax algorithm last week, you're going to see that, okay, the max agent does its maximization as before, but the mean agent right now is replaced with the chance node, and it returns the expected value of the state. So so this is the minimizer right now replaced with this, and you initialize V, and then for each successor you calculate the probability. How? I'm gonna explain about that in a bit, and then you add all those probability and come up with the value for that state, and finally you will return that value to the state. For the max agent, is the same things as in minimax. You take basically the max of the V that you have in that state with the value of the successor, and you return V. Okay, so this is the pseudocode of the algorithm, and if we wanted to apply that for this case, so this is our chance node right now. And this for this chance node, we said that we compute the expected value of the successor. So in here, you have 8, 24, and minus 12. And this is a way that you calculate that. It's the probability for 8, half, and then multiply that, and then you add it with this probability multiplied by 24, and this probability multiplied by minus 12, and you get the value of the state. So this is a kind of generalized version of that example. So you basically do the expectation for all these chance nodes, you get the number for all of this state, and then the maximizer chooses the value that is going to be largest between these 3 chance nodes. All right, so if you remember, you have learned about alpha beta pruning in min-max problem, right? So let's have this one, quickly take a look at that. So assuming that this is a minimizer node, not a chance node, then you basically choose the minimum value for a tree. That's the minimum value, and that's a optimal adversary. And then when you come down in here, your first value is 2. And then that value going to go to your minimizer. Then you're going to compare it with this and compare it with this state. And once you look at that number before basically do the comparison with this value and this value, you check the previous value of your alpha for this case, which is 3. You take a look at that value. If the current value V is less than your alpha value, basically you are not going to do the process for the rest of the branch at this state. So basically you prune these branches in here. But how about for expecting max? Is this possible for you to do this? So in expecting max, we basically calculate the average of all those states, and we have it in here. Right now, since we are calculating the average of those states, so what is the mechanism to prune those, prune the search tree to reduce the complexity? So the answer to this question is not very straightforward. To do the pruning, you need a bound basically on these states and the value of the probability for this one. So, and finding the bound is not a straightforward task. So, pruning is not easy in expecting max. Therefore, we need somehow to use some other strategy to somehow reduce the complexity of the algorithm. So basically, to do that, because in Minimax we kind of are using the depth first search algorithm. We choose we start from the root and we go down, down, down until we get to the end of the search tree. And if in expecting max we're going to do that until the end, somehow this task is impossible and we can't do that. That's the reason we needed to have the depth limited search, especially for expecting max where the pruning is complex. So for doing that, then we need some form of evaluation functions that work for our algorithm. And therefore, we need to come up with that evaluation algorithm for a given game. And that's not an easy thing to do. So one of the other things that we talked about was the probability, notion of probability in expecting max. So let's have a very quick reminder in probabilities, and then we continue our lecture. So in probability, we have a notion of random variable. Random variable represents an event whose outcome is unknown. A probability distribution, on the other hand, is an assignment of weights to an outcome. So let's take a look at this definition from an example point of view. So assume that we are taking a look at the traffic on a freeway. So we can define a random variable t as whether there is a traffic in the highway. And the outcome of that random variable could be 3 things. We can define it as 3 things. None means that no traffic. Light means that the traffic is light, like this situation. And then we are going to have heavy traffic like this. And then we are going to define a distribution function like this, like P, that is going to give us some value for all those events. So for example, probability of having an event of t equal to none means no traffic is 0.01. 0.25, probability of having light traffic is 0.5, and probability of having heavy traffic is 0.25. So basically, we defined a random variable, and we somehow calculate the probability of each event in this random variable. So these are some of the rules in probability. Probability always are non-negative, you know that, and then probability of all possible outcomes are sum to 1. So for example, in here, if you add all those probability, you're going to get the number 1. All right. As you get more information and evidence on those events, then your probability may change. For example, here, the probability of heavy traffic is 0.25. But the probability of having heavy traffic on the condition that we are kind of looking at the traffic at 8 a.m., then that is going to be 0.60. So this one basically is a conditional probability, and as you can see, the probability increased. And we might have some other conditional probability that the probability could decrease. All right, enough about probabilities. Let's have an example of probability in here of what we discussed. So for example, how long does it take to get to the airport? So that's one question that you might have. And we know that the probability of having no traffic is this one, heavy traffic is 0.5, and light traffic is 0.5, and heavy traffic is 0.25. You're going to calculate that, okay, you're going to go to the airport and you want to know how long it would take to get to the airport. Okay, so you need some other information here as well. So you need to know the duration of the time that takes you to get to the airport in these different cases in order for you to average the expected value. So we need to know basically P of the time that's taken you to get to the airport within this probability. If you assume that for no traffic, it takes you 20 minutes, for light traffic, 30 minutes, and for heavy traffic, 60 minutes, then the average probability is going to be the probability multiply all to these durations. And then you sum them up to get the average time that you basically need to know before you make your move to the airport. So it's going to be 35 minutes. All right. Let's see. Okay, so we discussed we talked about probability and the use of probability in expecting max. And somehow we said that we need to know the probability of having move in all these directions. So somehow we need those probability. So how you could get to find, how you are able to get those probability. It depends on the game basically, or it depends on the problem that you are working on. So for example, for rolling a dice, if it's somehow involved in your game, the probability is somehow uniform distribution of all those events that can happen after rolling a dice. For example, 1/6. Model could be sophisticated and require a great deal of computation to basically compute the probability. It's not an easy task. But for now, we assume that we are given all those probability for all these branches under our chance node. So we have access to this probability. Okay. All right, so now we are going to have an example for this algorithm. So we are basically, for this example, we are assuming that we are playing against an adversary that 80% of time he plays optimally, but the rest is playing kind of randomly. So the question is that what research should you use? So for adversarial search, so far you learned two of them, minimax and expectimax. So this question related to the choice between these two. So your adversary acts 80% of the time optimally and 20% randomly. So the answer to that question is the expectimax. So you use the expectimax because we're gonna have your chance of getting a bigger utility in your process. Okay, how you would understand the probability? One of the ways is to simulate your opponent. You need to simulate your opponent and somehow predict his or her move, and based on that, you are able to somehow estimate the probability of choosing a different branch under that chance node. So simulating the adversary somehow is not easy, and if you want to do that for many nodes, then the process is going to be slowing down very quickly. So and basically this is going to be very different from minimax problem, where we are assuming that player chooses one action with 100% probability. All right, now common questions of modeling assumption. So we talk about probability and how to calculate those probability, and therefore we need to come up with a model in our game to estimate those probability, or to calculate the value of the state to have our next move. And then we have a notion of optimism and pessimism in our modeling. So then you're going to have a dangers of optimism. So if you think that your opponent is not going to be acting optimally, then you may come up with this, end up with the situation that your adversary is acting optimally and you didn't predict that, and therefore you end up with a bad result at the end. So we're going to have an example on this, how it could impact the end result. And on the other hand, we might have a pessimism, dangerous pessimism. So you basically see the things that you basically consider the worst case scenario in your game, where you should not. So here is an example that shows this scenario, optimism and pessimism in your modeling. So basically we have a Pac-Man that play against the adversary. So one, we have the adversarial ghost, and the other one is a random ghost. So let's run these 4 different cases and see the score after each run. Okay, before I run this different simulations, just think for a minute which case we are going to get the higher score. So the question is that we want to know the score of this game when we run, for example, the Pac-Man run, the minimax problem, the minimax algorithm, but the ghost is adversarial. Basically, we run the min-max algorithm. We want to know what the score is going to be. And we want to know when we run the min-max for Pac-Man, what the ghost is random. What is the result in here? And then what if the Pac-Man runs the expect max algorithm? What's going to be the result in here? We don't want the exact value of those scores. We wanted to know which score is going to be higher. So we want to know that. And is it possible to have an estimation of the final value in terms of the largeness of the number, not the accurate value of the number? So which one is going to have the highest score when we play against the adversary according to this algorithm? And anyone have an answer for this question? Which game is going to be getting the maximum score?
Expect max Pac-Man with the random ghost?
Expect max and the random ghost. This one. Okay. Okay. And any other answer? How about this one? What is the score for this situation compared to this? So here the notion of pessimism and optimism can be explained. So let's run the algorithm and see if the answers of your friend is correct. So here is the random ghost, as you can see, just playing around. And then we are running the expect max Pac-Man. So it means that we run the right algorithm, because for the expecting max, you are assuming that the player somehow, the player on the other side somehow act randomly. So this is a good pair for this situation. Now let's see the other one. So this time we have the adversarial ghost and we play the min-max Pac-Man. This is also a good pair because we are assuming that our ghost is playing optimally and we choose min-max algorithm that takes that into the account. So we know that he's playing optimally and therefore we plan accordingly. So you see that the ghost is following the Pac-Man, and then Pac-Man chooses the longer route and he moves away. And finally, it reaches its objective. This time, 493. And this time, the ghost is adversarial, and Pac-Man is using the expect max algorithm. So Pac-Man assuming that the ghost is somehow act randomly, but the real situation is not. The ghost is basically planning and is playing optimally. So this is the case that Pac-Man is somehow optimistic in his game, and there's a danger for it. So this time he got lucky. All right, this time we have random ghost, and then the algorithm is minimax. It means that we are assuming that the ghost is acting randomly here and there. It doesn't follow the Pac-Man or do anything useful. And the Pac-Man basically assume that it is adversary and try not to get close to the food palette. So this is the situation of being kind of pessimistic and therefore getting a lower score. So here are the results, as your friend has mentioned. So the best case result is this one. Then Pac-Man runs expect max algorithm, and the ghost is somehow random. So these are the good two pair when you're running the algorithm. And these are also good pair. But since this is a dangerous world, Pac-Man get lower score. And in here, it gets higher score. And in here, also Pac-Man won 5 out of 5, and the average score was 493. As you can see, the score is somehow bigger than this because the ghost or the other player is not acting randomly. But in here, Pac-Man was somehow optimistic. It didn't consider the danger of having an optimal adversary. It didn't take that into account. Therefore, it loses 4 times in the game, and the score of -303. Okay, so let's talk about the other type of the games. So far we have talked about the games that involves the 2 players. One player is playing optimally, and the other player in min-max also playing optimally. And the second type was that we consider randomness for the two players. Let's see if we can have other type of the games. So we have mixed layer types for the games as well. So when you have your maximizer, then you might have a completely random event in your game. And then after that event happened, then you have your opponent having his or her move. So an example of that is backgammon game. Then before each move, you have to roll 2 dice in a game. So you do that. You basically roll 2 dice, and then based on the numbers that you get on your die, then you're gonna be having your next move, and your opponent also do the same. Therefore, we have here 1 layer of complete randomness in our search tree. Okay. So this is basically example of the Pac-Man, and since you're going to dice roll, then the number of basically searches or states that you are having is related to the number of moves, and also the depth of the algorithm that you are going to run. Since you have so much move in here, for depth 2 algorithm, that the number that you are going to have, the number of nodes, is going to be disordered. So as you can see, the number is too large, and therefore having 1 more depth, then this is going to get out of control. All right, so one note in here. So TD Gammon was an AI-based player that it only uses a search tree with two layer, and the evaluation function and reinforcement learning. It was a world champion level play actually for this game. And as you can see, the depth for this game is not going to be very important because the number of states is too large. And when the number of states are going to get too large, then the probability of having each of those states is going to be too low. And therefore, the usefulness of the search tree as you go down is going to diminish. So as you can see, the depth 2 algorithm for this game is going to give you a good estimate if you have a good evaluation function in the game. So therefore, cutting all those layers is not going to hurt the result of the game that much. Okay, the second type of the game that we are going to talk about today is the multi-agent games. So last time, so in previous example, we had 2 players in the game. Right now, we are going to have multi-agents game situation when instead of like 2 players, you might have 3 or more players. For example, in here, we are having 3 players. So we have a red player, blue player, and a green player. Each of these players are going to maximize their own utility. So what's the difference between the game with 2 players? So the difference is that the terminal nodes, instead of having a single value, right now they're going to have utility tuples. Basically, each node has its own value in this tuple. For example, for the red player right now, the utility at this terminal node is going to be 1. For the blue player, the value of the utility is going to be 6. And for the green player, the utility value is going to be 6 as well. So in this game, the players somehow are not adversarial. So they are only looking for the utility that somehow maximizes the end utility value. So they don't care about the utility of other players. But somehow this could create competition or collaboration in random. For example, in this branch, the green player is going to choose this terminal. As you can see, the tuple is going to 166. And somehow you see that the value of the utility for the blue player also is maximized. But player green doesn't care about that as long as it gets its own maximum value for the player. Okay. So let's run this algorithm to give you some idea, because in the assignment you have something similar to this. So the green player is going to choose this one in here. So we're going to have 166, and in here the green player is going to choose 162 because it's going to maximize its utility. In this branch, the green player obviously going to choose this one, 517, and in this one, it's going to choose 5, 2, and 5. And now this is the time for player B to choose its maximum utility. And for this branch, it's happened to be 166. And for this one, it's happened to be basically this one, to it compare the value of 1 with 2, and therefore it chooses the tuple that maximizes its utility. So it's going to be 5, 2, 5. And finally, the red player is going to choose, so this one, the blue player is going to choose 5, 2, 5. Okay. 5, 2, 5. And red player is going to maximize its own utility. So this one is 5, this one is 1. Therefore, the final value is going to be 5, 2, 5. Okay, so we talked a lot about utilities, and now is the time to talk about how we can basically define or compute those utilities in our game. And in expecting metrics, we said that we need to kind of average utilities. And so the question is, why not using minimax? why do we need to do all these things and not simply use minimax? So the answer is that in reality, normally we have randomness in our game. Therefore, a good strategy is choose the expect max algorithm to solve this kind of search problem. And for that, we are going to arrive at the principle of maximum expected utility. If you remember at the beginning of this course, we said that we are going to design rational agents. Those rational agents we define as an agent that their action are going to maximize their expected utility, given their knowledge. So that's the term that we have defined at the beginning of this semester, and therefore each agent that we design need to maximize its expected utility. So the question, where does utility come from? How do we know such utility even exists? How do we know that averaging even can make sense? What if our behavior preferences can't be described with these utilities? Before answering these questions, let's take a look at utilities for the two different search algorithms that we learned so far. One is the minimax and the other one is the expectimax. So first thing, we want to know whether how utilities are going to impact our final decision, and whether for minimax or expectimax, the result is going to be kind of catastrophic in making the final decision. So assume here that we have minimax algorithm is running, and then somehow we decided that to square all those values at the terminal node, and we want to know how this is going to impact our final decision in min-max problem. So if you take a look at in here, min-max is going to choose 40 here. Sorry, so that's a minimizer. It's going to choose 0 here. This one is going to choose 20, and therefore the final value is going to be 20. And therefore the route that we are going to take based on this result is this right route. And when we square those values, again, here we are going to get 0. And here we are going to get 400. And as you can see, 400 is going to be at the root node. And therefore, we are going to take the route to get that utility, which is the right-hand side. Okay, now let's see how the definition of this utility function is going to impact the expectimax. So as you could see for the first example, somehow min-max is insensitive to this monotonic transformation. How about the expectimax? How sensitive is going to be to the definition of this utility function? So now we have the chance node instead of the minimizer in this layer. These are our chance node. And therefore, instead of taking the minimum value of those, we are going to have the expected value of those terminal at these states. So if we are assuming that we have like equal probability for these terminal nodes, and the value at this point is going to be 20. Then 20 plus 30, 50 in here, you're going to have 25. Therefore, 25 is going to be assigned to the root. To get to that terminal, we need to take this route. And let's now square the value. We get these values. And then we are going to run again the expect-max algorithm and see the result. Is it going to be right or going to be left? So here we are going to get 800. Basically, that's expected value of these two with equal probability, half multiplied by 0, half multiplied by 1600. That's going to be 800. And here, so we have 400 plus 1900. And since the probability are equal, then you divide it by 2, 1300 by 2, and then we get 650. So we get 650 for this branch and 800 for this branch. So 800 is going to be the winner. Therefore, we are going to take the left route. As you can see, Expectimax is not insensitive to monotonic transformation, and having different utility at the terminal node is going to impact the decision-making process at the roots. All right, so now since we know the importance of the utilities, so let's have a formal definition of these utilities for this search game. So basically, utilities are the function, are a function from outcomes that are a state of the world, to real numbers value that describe an agent preference. For example, here an agent could have an ice cream. So the first one could have an ice cream cone. So you could assign utility function of 0 for this. And then you could have an ice cream with 1 scoop. So the utility function can define as 1. And then you can have utility functions that kind of give the real number 2 when you have 2 scoop of ice cream at agent hand. So this basically, this is a function from outcome. The outcome, if the outcome is this, to real numbers. Our real numbers now are 0, and 1, and 2. So that's as simple as this. So for different games, we could have different utilities. For example, in here, for tic-tac-toe, simply we have +1 or -1 as a utility function. All right, so utility summarizes the agent's goals. So basically, we need numbers to work with computers, and that's is going to solve these issues, this issue for us. So there's a theorem that says that any rational preferences can be summarized as a utility function. All right, no matter how complex is that preference could be. So you can define a function to create those real numbers for you. All right. So one important thing in creating the utility functions is that you not only consider the outcome of your basically action, you also need to consider the probabilities of having those outcomes. Therefore, there's a notion of uncertainties that you need to be taken into the account. Then you define your basically your utility function. Here, getting an ice cream for example, if you have an agent that the objective is getting an ice cream. So get the single scoop of ice cream, we have this branch, and if we get the double scoop of ice cream, then we are going to come to the right branch. So we get the single ice cream, we assume that that's going to happen with 100%, 100% of the time, and therefore the agent is going to be happy. But when we get double scoop of ice cream, then there's a possibility of those scoops falling down, and or basically the agent could enjoy the 2 scoop of ice cream. So in defining the utilities, we need to have these cases also into the account, so that in our decision-making process, we could basically decide better. So we talked about preferences. We said that these preferences can be represented in real numbers. So let's define some notation for it, and then define a systematic strategy to define those preferences and find a relation between utilities and preferences. So to formalize this, to basically formulate this problem for preferences, we have a notion of prices. So prices could be price A or price B or some other prices depending on. Then we have the notion of lotteries. Lotteries are situations with uncertain prices. For example, in lottery L, you could get price A with probability P, or you could end up with price B with 1 minus that probability when there are only two prices. Then we have a new notation here. So A greater than B means that agent prefer A over B, and this tilde sign means that A is indifference. The agent is indifferent between A and B, so it doesn't matter which choice. So preference and indifference. So remember this. So we have the price A, and then we have a lottery, A lottery. So we could end up with price A with probability P, or we could end up with price B with 1 minus P probability. So this is our lottery. And then rationality, normally for rationality, you're gonna have like multiple plans, plan A and plan B. To be a rational agent, you need to consider all those consequences in your decision-making process. So we said rational agents, therefore we need to define some framework to say which agent is rational, acting rationally, and which agent is not acting rationally. For that, we need the axiom of transitivity. So this axiom said that an agent could prefer A over B. So let's define it again. So if an agent prefer A over B and also prefer B over C, then that agent will prefer A over C. So that's the transitivity. So let's see if this axiom is not followed by an agent. What is going to happen? If you have an agent, right? If you have an agent that prefer B over C, and then it wants to get like the B, price B, and exchange it with C and pay 1 cent for it. So it's pay 1 cent and get basically B. And then the agent again prefer, for example, A over B, therefore it exchange the price A with B, and it's paid 1 cent for that. Now the agent have B, but it wants A, and therefore it's exchanged with B, but he pays 1 cent. So, and your agent may prefer C over A, therefore it's going to exchange A with C and basically pay 1 cent. So right now, at this point, the agent had C value, right? And it said change it with B, pay 1 cent. Exchange it with A, it pay 1 cent. And exchange it with C and it pay 1 cent. So as you can see, at the end, the agent end up with price C, but it also pay 3 cents. So basically it loses 3 cents, ending up with its own first price. Why this happened? Because this agent didn't follow this axiom of preference, which is axiom of transitivity. So why? Because the agent says that it likes A over B and B over C, but in here it says that it also prefers C over A. So that's the reason we call this agent irrational. Therefore, in basically making our agent in order to act rationally like us, they needed to follow these axioms. So this is one of the axioms. So let's take a look at the other ones and see how you could basically read these mathematical expression and translate it in real life in practice. So the first one is orderability. So agent could prefer A over B or B over A or B indifference between A over B. So that makes sense. You prefer A over B or B over A, then basically you are indifference between A and B. Transitivity is the one that we just discussed. And then we have the notion of continuity. So if an agent somehow prefer B somehow between A and C, then there should be a lottery between A and C with some given probability P, which is in difference with B. Meaning that you can make a lottery between A and C such that you could be indifferent with that lottery or choice of prize B. All right, so substitutability, if you are indifference between prize A or B, then there's going to be lotteries where A and B are involved with A and B are involved with probability P, where you are also indifference between those lotteries. So it doesn't matter for you or for the agent to participate in these two lottery when you are indifference also between price A and B. So the reverse is also correct. If you are indifference between two lotteries that involve A and B with some given probability P, then you are going to be indifference between price A and B. The other one is monotonicity, meaning that if you prefer A over B, then there are two probabilities, P and Q, where P is greater than Q. And basically you prefer to participate in the lottery between A and B with probability P that is greater than probability Q in the other lottery involving A and B. So the reverse is also correct. So if you prefer a lottery between A and B with given probability P, then it means that you basically, at the result of this, the probability of P is going to be greater than Q. Okay. If you have any question about this axiom, please let me know. These are a bit confusing. These were not anywhere in our kind of math courses before. Any question about these axioms? All right. Okay. So in case you have a question about this later on, just let me know. These are the only, I guess this is the only part of this lecture which is a bit involved in math. Okay. So okay, if an agent follow all these axioms, then we can give him the rationality stamp. Basically, when we are designing our agent, we have to make sure that all these axioms are applied in order to call the agent a rational agent. All right. So there's a theorem. It says that given a preference satisfying these constraints about that we talked about just now, then there exists a real valued function like u that the utility of A, price A, is basically greater than utility of price B if the agent prefer A over B. Basically, we have been talking about the utility function. Now, we understand the notion of preferences between different prices. It says that if the agent prefer A over B, when you define your utility function, it should or it must somehow follow this equation. This means that your utility function should be greater than utility function A should be greater than utility B if you want your agent prefer A over B. And then we have the utility of the lottery is the expectation of the utilities. So this is the way that basically we define the lottery. So meaning that for a given lottery involving price S1 to price Sn, with probability 1 for price S1 and probability n for price Sn, then if you want to calculate the utility of that, is going to be the sum of basically the expectation of those utility function for each of these prices. So if you take the utility of each price and then multiply that with probability of that given price, and then if you add them up, then you basically compute the utility of that lottery.